7.1. Chapter 7 is on differential equations. So today we're talking about what a differential equation is. We are looking at how to verify if a function is a solution to a differential equation, and then also how to find particular solutions to differential equations. So one thing I do want to say with today's lesson, and especially if you are working on the practice for the lesson, guys, I need your attention up here, please. If you are working on this practice, I would say the toughest thing about this particular section is reading a question and figuring out what they're asking you to do. Once you know what it's asking you, it's really not too bad. And I'm not just saying that, but some of these questions are just worded so oddly. You need to make sure that you can understand what they're asking you to find. Because if it's asked on the AP test, it's going to be the same thing. You have to know what they're asking you to find. So what I have at the beginning, I want to, really, these aren't examples, but in 7.4, we actually go into population growth and mass in more detail. So we're going to come back to these two applications later. I just want to kind of preview them now in terms of explaining what a differential equation is. And it does say at the top, this is considered one of the most important applications of calculus, is a differential equation. So first we're going to look at how population growth could be set up as a differential equation. So I'm going to set up an equation with you. Here in the population growth example or application, we are assuming the population grows at a rate proportional to its size. So that's the assumption that's made. It's growing at a rate proportional to its size. So our two variables for population growth would be t and then p. So we let t represent time, and that is the independent variable. We let p represent the number of people or animals in the population, so population. And that would be the dependent variable. We could also write p as p is a function of time, so p of t. So here I will say with differential equations, not for every single one, but for a lot of them, Leibniz notation is used. So what does dp dt mean? Yes, the instantaneous rate of change of population with respect to time. This is p prime of t. That would be another way to write it. Okay, so this is, now since we're talking about population growth, this would be the rate of growth. Okay, so here's the differential equation that would tie into this example, and it comes from the assumption that population is growing at a rate proportional to its size. So the derivative, dp dt, is proportional to the function p of t. So we can write it like this, dp dt is equal to some constant k, they use the constant k, times p. And this is considered a differential equation. I am defining this later. A differential equation is an equation that involves a function and one or more of its derivatives. So we have a function p, or p of t, and we have its first derivative, dp dt. That's what makes this a differential equation. Like I said, in 7.4, we come back to this and we talk about this more. I'm just kind of previewing in terms of explaining what a differential equation is. But as we come back to it, I just want to say here, K is called the proportionality constant. And then because we're talking again about population growth, we're assuming the rate, the population, K, everything's positive as well. Here's what I want you to think of though. And this is just going to be, well, kind of reasoning through this without knowing the, I guess, mathematical way to do it, because we don't get to that until 7.3. Looking at this differential equation, a solution to a differential equation is any function where when the function is plugged in along with any of its derivatives, that makes this equation true. So since this is saying the first derivative is equal to a constant times the original function, can anyone think of a function where its derivative would be proportional to itself? Okay, e to the x, because the derivative of e to the x. Well, x to the third, though, the derivative would be 3x squared. So it wouldn't be, you'd have an x cubed and an x squared. But what Connor said, e to the x, because e to the x, the derivative of e to the x is itself, or rather any exponential function, the derivative is always proportional to itself. The derivative of an exponential function is an exponential function. The actual solution to this, or the form of all solutions, we're not looking at the mathematical way of how to figure this out right now. We're just thinking through it. Any solution to this would be in this form. P of t equals c times e to the kt. But it is a form of the function e to the x, or e to the t. So just getting you to think about what function would have a derivative proportional to itself, an exponential function would. This ends up being the form the solutions are in. In 7.4, we'll see why. Yep.
You were right. That's why it's going on the naval chasm. That's why it's going on the naval chasm.
In the way this one is set up, it would only be the first derivative is equal to it. But we do have some differential equations where this might be the second derivative, which then a trig function could work. So yeah, so then another application we look at deals with mass. Now this is dealing with motion of a spring, a mass of an object at the end of a vertical spring. Some of this I have on here so you understand how it's set up. But again, really what I'm trying to look at is why it's set up as a differential equation. And then we're again going to think about what a solution could be. So this says by Hooke's law, which you don't need to know in this class what Hooke's law is. But it says if the spring is stretched or compressed x units from its natural length, it exerts a force that's proportional to x. So the formula that goes along with Hooke's law, the restoring force, which we could call F, is equal to negative k times x. So x here is actually representing its x units from its natural length. So x here would be representing position. So it's showing here kind of what x is representing. And x, again, would be a function of time. It'd be x of t. X is your function. But this is the formula that goes along with Hooke's law. You don't need to have that memorized for any reason in this class. In this formula, though, K is called the spring constant.
Did I not say that, Jared? Jared, please tell me I said that.
Okay, so then setting up to see why this is a differential equation or how we could set this up as a differential equation. What is Newton's second law? Any physics people in here know?
Yeah, that's why I knew it was spring constant. Yeah, I did know that.
No.
That was the acceleration. You can quit flicking me off.
Yes, force equals mass times acceleration is Newton's second law.
Yeah. Let it fly.
Again, you don't need to have this memorized for the AP calculus test. So the formula is F equals ma, or F equals m times a. I'm going to flip that around. Okay, I'm just flipping the two sides. And then what I can do here is substitute in F is equal to that negative k times x. And remember, x is your function. X is a function of time. As this is written right now, it doesn't look like a differential equation. There's no derivatives in it. However, if x is representing position, what is acceleration compared to position? The second derivative. So I can write acceleration as the second derivative of x. And again, in Leibniz notation, it would look like this. M times the second derivative of x is written this way. D, it looks like dx squared, yep, over d squared t. That's what it looks like. That's not how you actually say it. This just represents the second derivative. And then this is equal to negative kx. So here's your, actually I think I wrote this backwards. This should be, sorry, this should be here. I put the 2's in the wrong place, I'm sorry. Did you forget it the first time around? Oh, forgive that. Sorry. Okay, so this would be representing, or this would be a differential equation. You have a function x of time along with its second derivative. The mass would be constant. K is a constant. This is where, if I wrote this a different way, again, this is using reasoning and what you know about derivatives. You're not going to have to guess solutions throughout this chapter. If I wrote this a different way, if I divided both sides by the mass, because the mass is a constant, I could write it this way as well. So the second derivative equals negative k over m times x. What this is saying is kind of what this said up here. This said the first derivative is proportional to the function. This says the second derivative is proportional to the function, but it's the opposite sign. So Dalton, this is what you were asking about, the second derivative like of sine or cosine. If you take the second derivative of sine, it's negative sine. That's where sine and cosine would be solutions of this. So some variation of the sine or cosine functions would be a solution to this one. So it's kind of understanding what functions would work. I know this is switching back into your mindset of derivatives. We were just in antiderivatives and we're kind of switching back. We deal with derivatives and antiderivatives in this chapter. So your mind is going both directions in this chapter. So in general, a differential equation is an equation that contains an unknown function and one or more of its derivatives. So if you have a differential equation that has x and y as your variables, it would be an equation that would contain x, y, and then any derivatives of y as long as y is a function of x. A differential equation has what's called an order. It's kind of like the degree of a polynomial. So the order of a differential equation is the order of the highest derivative that occurs in the equation. So this first example, the population growth example, would be a first order. This would be a first order differential equation. The highest derivative is the first derivative. The second example we wrote would be a second order. The highest derivative is the second. So you're not asking questions, what order is this differential equation? But if they say in a problem, the third order differential equation, just for you to understand, that means the highest derivative is the third derivative. That's helpful to know. So like I said, it's kind of like how you would describe the degree of a polynomial. It's the highest derivative. A function, so your solutions to these are functions. So the function y equals f of x is a solution of a differential equation if the equation is satisfied when the function itself and its derivatives are substituted back into the equation. Solving differential equations, I will say, not every differential equation can be solved. Really. So,
you know, when you brought up the physics, I was like, oh, I got this in the back. And now it's just like...
Today you are just verifying if a solution is a different, or if a given function is a solution. You are finding particular solutions. In 7.2, we're using graphs to make conclusions about a solution. 7.3 is where we look at a specific type of differential equation that can be solved. But not all of these can be solved by hand. We actually have already solved some differential equations. So I have an example on here of a differential equation that you should be able to solve. If I gave you this differential equation, y prime equals x cubed, and you try to find a function y that would be a solution to this, anyone know what y would be? 1/4 x to the 4th. Okay, if the derivative of a function is x cubed, you're thinking, what function has the derivative x cubed? You're taking the antiderivative. So you have already solved some differential equations. We just didn't talk about them as differential equations. Okay, this here would be a particular solution. If it asks you for the most general solution, you would have to include the plus c. Yes, this one is more specific than this one. This is saying your c value is 0. This one is saying your c value could be any constant. And your general solution, some of the practice problems might talk about families of functions or families of solutions. So you could actually graph a family of general solutions just by substituting in different values of c. So graphing 1/4 x to the 4th plus 2, 1/4 x to the 4th minus 3, and then just seeing the difference between all of those graphs. So if a family of solutions or a family of functions is referenced, that's what they're talking about. Okay, here we'll actually get to some examples. All of this information may or may not have been confusing. We'll clear some things up. Here's what you will be working towards today. It says, for example, 1, it gives us 3 different functions, and it says determine whether the function given is a solution of this differential equation, y double prime minus y equals 0. To determine if it's a solution, you are substituting in the function itself and any of the derivatives that are in the equation. So where I see y here, I would substitute in sine of x. But before I substitute this in, I would need to know what y double prime is. So I can substitute that in as well. So if I have y as sine of x, what would y prime be? Cosine of x. What is y double prime? All right, so then I substitute in y double prime. So I would have negative sine of x minus y is sine of x. And I want to know, does that equal 0? I'm seeing some no's. This is negative 2 sine of x. That does not equal 0. So therefore, well, then you'd be solving for x. So when you're finding, it's saying, is this function a solution? So you're not, when you're solving these, you're not looking for an x value, you're looking for a function. So this is therefore not a solution to this differential equation. So I would just say here, no.
No.
Because when I substituted in y double prime minus y, I did not get 0. All right. Why don't you check B and C? Check if those two functions are solutions to that differential equation.
I'm sorry. Yeah, you guys got the wrong number. My boy, 11 or so. Yeah, click on. Right. The second one? The first one. Yeah. Right. 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 Yeah. So it's yeah.
Oh.
Because we did a negative. I know it's true because we are just in the shape of so that's yeah, but if you do it twice, it just changes the stuff. Oh yeah, yeah, but that's what I mean by well, you know how if you have I don't know, so it's negative one. Like for the first one, before you I had it built up in my head.
But realize part of your AP test, then you apply those multiple choice, and that applies to the response. Or if they look at your work.
Oh, so got it.
You want to know why it's right.
I did. You're not going to understand. I'm like, file some. Have you seen that video? Yeah. If for now. No. No. I would like physics. You like Jimmy Buffett? Yes. No way.
All right. This is what I was making sure of, and I need to stress this.
Your husband's an artist?
I need to stress this when it comes to your AP test. I know I've said it before because some of you have been repeating it back to me. When you have a free response question, they do not just look at your answer. For some questions, to get full points, you have to have the correct work written down as well. Sometimes you can have the correct answer, and you might get a point for that, but if you don't have the correct work to justify your answer, you won't get the point for the work. Or you might not get any points if they don't see the right work, they might disregard your answer. So, I was particularly looking at letter B. Remember, or rather, don't forget chain rule with derivatives. I know it's been a while since we've just focused on derivatives. The derivative of the outside for e to the negative x is itself, you have to multiply by that -1. So that's what I wanted to make sure when I walked around, that's what I was checking. But these two do end up being solutions. This here would be a particular solution. This here with the C would be a general solution. So C could be any number, and it would still be a solution. So the next part of this says, and we've kind of done some of this already as well, In a lot of cases, we're looking for particular solutions, not general. So you're given some sort of initial condition to find what C would be. This is called an initial value problem when you're finding a specific solution based on an initial condition. So example 2, we are given this differential equation. It says verify that the function y equals c times x cubed is a solution, and then find the particular solution that satisfies this initial condition. So first of all, we are going to do the verifying part. Okay, we have our differential equation. And before we actually start plugging things in, we need to know based off of what y is, what y prime is. So if y is cx cubed and c is a constant, what would y prime be? 3cx squared, or c times 3x squared. Okay, so then I can substitute in y prime and y into the differential equation. If you have an x in your differential equation, that just stays x. So I would have x times y prime is 3cx squared minus 3 times y is cx cubed. And I want to know, does that equal 0? So if I multiply here, I get 3cx times x squared is x cubed. Here I would have 3cx cubed. I do get 0. So yes, I have verified that this general solution is a solution to the differential equation. Okay, that's the verifying part. That's what you just did in the previous set of examples. Now to actually find the particular solution, we have this initial condition. This shows the x value is -3, the y value is 2, or when x is -3, y is 2. So when you're trying to find a particular solution, you start with the general solution it gives you, and your goal is to find the value of c. So I can substitute in -3 for the x, 2 for the y, solve for c. So I'd have 2 equals c times -3 cubed. Which then if I simplify, -3 cubed is -27, so -27c. Divide by -27, I get -2/27 as the c value. And then you have to substitute that c value back into your general solution. So the particular solution is y equals -2/27 x cubed. So you've done problems like this. If you think back to 4.9 when you first learned antiderivatives, and then I gave you an initial condition, you had C's, sometimes you had D's you had to find, but you were substituting those coordinates in to get the constant values. That's what this is. Question, Connor?
So are you assuming that we're going to instead of
You'd have to see if it would still satisfy like the differential equation. It might not satisfy that. Correct. Yep, you're going off of exactly what they gave you and finding C from there. So in a way, compared to what we did in 4.9, you're doing less work because they're already giving you what you substituted into, if that makes sense. We did more work in 4.9. All right, and then example 3. I included this. Sometimes you might see questions like this one. For what values of r, so our answer is going to be r values. For what values of r does the function y equals e to the rt satisfy the differential equation y double prime plus y prime minus 6y equals 0? So what we need to do is we have y. We need to know what to substitute in for y prime and y double prime. So if y is e to the rt, what is y prime, or how would we find it? Okay, so this again, chain rule, it would be e to the rt is the derivative of the outside multiplied by r. So it would be re to the rt. So yes, the r in a sense comes down in front, but the r also stays in the exponent. Don't remove it from the exponent. Yes, with respect to t. Yeah. And then what would y double prime be?
R squared or
R squared e to the rt. Okay, so then substituting those into this equation, we have r squared e to the rt plus re to the rt minus 6 times y, which is just e to the rt, so minus 6e to the rt equals 0. We are solving this equation for r. We're trying to find the values of r that make this equation true. How do we solve this for r? Ideas. Factor out an e to the rt. They all have an e to the rt. So if I factor that out, I then have r squared plus r minus 6, which is quadratic. So really what I'm doing from here is I'm setting e to the rt equal to 0 and the quadratic equal to 0. Possibly, yes. E to the rt equals 0. Why? Yep, e to a power will never equal 0. You could try to solve this by taking natural log of each side. You cannot take the natural log of 0. So this does not have any solutions. Okay, so the only solutions are coming from the quadratic. How do you solve a quadratic? Quadratic formula or the factoring. Yeah, if you do the diamond or the x. So, you know, some of you do this. You're multiplying to negative 6, adding to 1. 3 and negative 2. R plus 3 times r minus 2. So then the values of r that satisfy that differential equation are the r values negative 3 and positive 2. And that means the two particular solutions would be, one of them would be y equals, I know it doesn't ask for this, but y equals e to the negative 3t would be a solution, or y equals e to the 2t would be a solution. So that's what that would mean. Okay, so there is practice here. Not that I don't recommend all practice, but make sure when you look at these questions, you can figure out what they're asking you to find.